All right, in this video, we're going to take a look at the chain rule. What is the chain rule? Well, this is what we use when we want to take the derivative of a composite function. So let's recall what a composite function is. All right, so f of x is a composite function if there exists a g of x and h of x, so function g and a function h, both in terms of the independent variable x, such that f of x is equal to g composed of h of x. So we apply g on the function h of x, and that is how f of x is defined. So if f of x is defined like this, we want some kind of rule in order to know how to derive this type of a function. And that's exactly what this chain rule is. So we'll go ahead and write that down now. So the chain rule is the following. That says that if h is a differentiable function at x and g is a differentiable function at h of x, then the composite function f of x equal to g of h of x is differentiable at x and furthermore, what is that derivative? Well, that derivative, f prime of x, is equal to g prime of h of x. So the derivative of the g function, and then evaluated at h of x, times the derivative of the h function. In Leibniz notation, so this is in Newton's notation where we're using primes. In Leibniz notation, if we write this as y is equal to g of u, where u is the function h of x, so if these two things are both differentiable functions, then dy dx is equal to dy du times du dx. And so either of these are how we can think about the chain rule. And I mean, they're the same thing, right? We have the derivative of the outer function evaluated at the inner function times the derivative of the inner function. And that's exactly what this says as well. Y is equal to g of u, so y is a function of u. Take the derivative of y with respect to the variable u, and then we multiply that by the derivative of u with respect to x, which u is h here. So we see that these are the same, just the two different notations for them that we're used to using for derivatives. Okay. Now let's think about this, right? This function should be intuitive, right? So what if we had said that the change of u, right? U is this function h of x. What if that u changes twice as fast as x? What does that mean? That means du dx is 2. And what if y changes 3 times faster than u? Well, if that's the case, if y changes 3 times faster than u, and u changes 2 times faster than x, then how many times faster does y change than x? Well, that should be 6, right? We should just multiply those things. And that's exactly what the chain rule here says. So really, this is also intuitive here. So let's go ahead and write out or say one more thing here, and then we'll do a couple of examples. And really what we want to say is, actually looking back at this formula, that again, we think of this chain rule as the derivative of the outer function, right? We had an outer function g here of our composite function, and then the inner function was h. So our derivative of f of x is the derivative of the outer function g times the derivative of the inner function h, just with the caveat that g, the derivative of g, is evaluated at the function h. So with that in mind, let's let that be how we think about solving this first example. So example 1, let's find the derivative of 3x squared plus 1 quantity squared. So here, the outer function is u squared, right? We have some quantity here squared. And so this tells us that h of x, our inner function, is 3x squared plus 1. So let's do the chain rule now. So the derivative of quantity 3x squared plus 1 squared is 2 times u, right? What's the derivative of u squared? That is 2 times u. But then we have to multiply by the derivative of u with respect to x, right? Where again, u is this h of x, which is the 3x squared plus 1. That's our inside function. So our derivative of u squared is 2u times du dx here. That's what our chain rule says. We take the derivative of the outer function, which is 2u, times the derivative of the inner function, times the derivative of u. So we get 2u times du dx. Well, this is 2 times u, which is 3x squared plus 1, times du dx. What's the derivative of 3x squared plus 1? That is 6x. And we could generally stop here. But for the sake of seeing that we did everything correctly, let's go ahead and multiply all of this out. This is 12x times 3x squared plus 1. So 12x times 3x squared plus 1, and we get 36x cubed plus 12x. Now let's do this derivative in a different way. Let's first multiply it all out. So notice that 3x squared plus 1 quantity squared is equal to 3x squared plus 1 times 3x squared plus 1. Just to clarify what we're doing here, we're just checking this as our solution to the derivative here. That's all we're doing. So what is this? 3x squared times 3x squared is 9x to the 4th. And then we have 1 times 3x squared times another 1 times 3x squared. So this is plus 6x squared plus 1. So now let's take the derivative of that. What is the derivative of 9x to the 4th plus 6x squared plus 1? Derivative of 9x to the 4th is 36x cubed. Derivative of 6x squared is plus 12x. Oh, and we see that we got the same thing. So maybe that'll help you believe that what we did here was correct. Let's go ahead and do one more example where we just use the chain rule. So let's find f prime of x when, so find f prime of x when f of x is equal to sine of x squared plus x. Well, what is our outer function? Our outer function is sine of u. Outer function is sine of u. And what's the inner function? That is x squared plus x. So the f prime of x here, our f prime of x, is the derivative of the outer function. What's the derivative of sine of u? Well, that is cosine of u times the derivative of the inner function, which is 2x plus 1. And of course, we replace all of our u's and put it all back in terms of x, right? What is u here? U is that inner function, so x squared plus x. So this is really cosine of x squared plus x times 2x plus 1. All right. And that is it. All right. And that will actually end our video as well.